Okay, this week we're going to start talking about how the Earth gets its energy. Uh, the Earth gets its energy from the sun. It's as simple as that. So, all the energy the Earth receives comes from the sun, pretty much. That is the main source of our energy. And the atmosphere is driven by that energy. So, how does this energy flow into the Earth's atmosphere system, maintains the Earth as habitable so we can live here, and still keep a balance of that energy? I mean, the sun's throwing out radiation at us and energy at us all the time. So, how are we staying the same? There's very little variation in our overall temperatures of the Earth relative to the amount of sunshine that we receive. So, let's take a look at some of that. So, we'll start with how we get the energy. The energy comes in electromagnetic waves. What are they? They're waves that move through the atmosphere or through space that carry energy. If you look at a microwave, it heats up. That's an electromagnetic wave that's causing that heating. So you can think of electromagnetic waves as literally being a wave in the atmosphere, and we can measure them. There's a wavelength. Wavelength is basically from one crest of a wave to the next crest of a wave. I like to think of it in the ocean. When I'm out swimming in the ocean, I have a wave hit me that kind of knocks me around a little bit. That's one crest of that wave. The next crest will be, then it'll go down. I can stand up real well, and then all of a sudden another wave hits me. That's the wavelength, the distance between those two crests. And the frequency is how fast, how many of those waves pass you in a certain period of time. Now, the one thing that's different between the ocean and electromagnetic waves is all electromagnetic waves move at the speed of light. So they're really moving along. 300,000 kilometers per second they move along. So that the faster they're coming by, the more energy they hold. So that shorter that wavelength and the higher the frequency is that they're passing you, the more energy they hold. So the sun, being tremendously powerful, and it's really, really cold, really, really hot, has a very high frequency coming out of it. The Earth is not as hot, so it has a lower frequency coming out of it. So you can see that there is a difference in radiation from the sun to what the Earth does. The sun is an ultraviolet radiation, ultra high frequency radiation. The Earth is infrared, below red, which is a lower spectrum of radiation. So there are some laws about the radiation. Did you know that the Earth is a black body? Most things are. You are a black body. You absorb radiation from the sun and you reemit that radiation back at some temperature. The Earth, whatever radiation it absorbs, it reemits that same amount of radiation back out. So it is considered a black body. And there are mathematical laws that define actually what the wavelength is that the radiation will come back out from the Earth or the sun based on that. And you can see that most of the radiation from the sun is in the visible spectrum. So God kind of gave us eyes to see the radiation from the sun, the visible radiation we see. Now, if you go on Earth, a lot of the radiation coming up from the Earth is infrared. And some of the radiation coming in from the sun was ultraviolet. So you can see the spectrum here of radiations that are coming into the Earth. There's another energy flux. Notice it's to the power of the fourth of temperature of whatever body is radiating. The Earth's temperature is significantly lower than the sun's temperature. So guess which one is going to radiate a whole lot more energy? And because of this law, way, way more energy. So a lot more energy is coming out from the sun than would radiate out of the Earth. So there's another law. So we have the sun at a certain position from us. We consider it 1 astronomical unit away. And with that, the amount of energy that is coming into the earth is 1 over the radius, the distance from the sun squared. So if you half that distance, you would have 4 times the energy that would come into that planet. If you multiply the radiance by 2, you'd only get 1/4 of the infrared radiation coming in. So there's a doubling or halving, whatever, depending on the distance you actually are from the sun. So you can see it really doesn't take long to diminish the amount of radiation coming from the sun as we move away from it. That's why Mars is so much colder than we are. So the sun, with all of its fabulous radiation that's coming into us, it doesn't come in directly. I want you to look at these 2 flashlights. If you were to look at flashlight A, notice how this circle is fairly intense and fairly bright. Flashlight B, circle's broader, not nearly as intense either, not as bright. Well, that is the Earth. Take the Earth as being if you're at the equator and the sun is directly overhead. We'll say it's March 21st. The sun would be directly over the equator. Just yesterday, the 21st of June, the sun was directly over the Tropic of Capricorn, 23.5 degrees north. So it would be that small circle right over that area. But think about it now, further north, we're getting more of this broad area. So the same amount of energy from the sun is spread out over a bigger area. So if you were at any individual point in here, you're getting less energy than at any individual point at the equator. Now, that's very important because this sun is going to move. It's going to head south in the wintertime and north in the summertime. So this spreading out is going to change, especially in our latitude. And that's significant because it changes the amount of energy that's coming into your house and my house every day. So with that, let's take a look at a little bit of how this all is going to change. So I really want to just show you the motions here. The Earth is tilted. So if the sun is at the equator, autumnal equinox or vernal equinox, the tilt is such that it's not facing the sun. It's facing at an angle away at the side of the sun, we'll say, up and down here and here, so that the sun is coming right into the equator. Now, wintertime, the tilt's away. Guess what? The sun is not even hitting up here in the north. Matter of fact, if you're at the North Pole or above the very northern tips of the country of Alaska and stuff, you're not getting any sun time at all in the wintertime. Summertime, the same thing is going to happen to the South Pole. Notice the other thing here. Look at the Earth. The sun doesn't, we don't rotate around the Earth nice and smoothly in a perfect circle. It's elliptical. So in the wintertime, we are actually a little bit closer to the sun than we are in the summertime. So actually more energy gets into the southern hemisphere in the winter and still some more in the northern hemisphere. If we had reversed this, if we were over here and this was our summer, well, then we would be much hotter in the summer. So you can see that little bit of an ellipse changes again the distribution of that energy throughout the solar system and throughout our planet. So with that, now that we've gone through getting all this energy in, there's something that's going to happen to it as we go here. And I wanted to show you that part too, because All right. Several things happen with radiation coming in. It's scattered, it's reflected, or it's absorbed. All right. So the total adds up to 100% is what's happening into the Earth's surface. A certain percentage of it, radiation, is absorbed either by the atmosphere or by the Earth itself, the ground. A certain percentage is reflected, the albedo, the amount reflected. And a certain percent is basically scattered around. So all those take effect in the atmosphere. So have you have a cloud up here or water droplets? The sun's radiation hits it, it just scatters it in all directions. And with all those directions, some of it's going to go back out into space, some of it's going to come back into the Earth, but not the total amount of radiation makes it in when it hits a cloud. And you can see that. Now, take an albedo. When you're outside in the wintertime and you have bright snow cover, real fresh snowpack, you need to wear sunglasses. The reason you need to wear sunglasses is that albedo is so high of snow, about 80% of the solar radiation coming in from the sun is being scattered back up into the atmosphere, away from you. That's why it stays cold after it snows. So finally, we absorb so much energy. That absorption takes place in the stratosphere. It takes place through ozone. It'll even take place all the way down at the surface of the Earth. So all of this begins to tell you how the energy, all this energy that you've come into and seen here, is distributed and is absorbed by the Earth, absorbed by the radiation. Some of it comes in through the oceans and absorbs the temperatures. Finally, you have the greenhouse gases. What are they? Now, there are gases basically that absorb infrared radiation. They don't absorb ultraviolet radiation. So the radiation from the sun comes in, then gets absorbed by these gases on the way back out from where the Earth reflects it out. Greenhouse gases are water vapor, carbon dioxide, ozone, methane, and there are others. So each one of these absorbs that infrared radiation from the Earth and then transmits it both up towards the sun and out of the atmosphere and back down towards Earth. That's what keeps us warmer. So the more of these greenhouse gases are here, the warmer we're going to be. The less of these greenhouse gases, the cooler we're going to be. So these are what allows the Earth to be habitable. I wanted to show you quickly, just looking at how the Earth, this radiation balance works. Here's Barrow, Alaska. There's no sunshine in the wintertime. And notice how the normal temperatures hardly change through March. Sun finally comes back in March, and boy, they shoot upwards. Also, I wanted to notice here's minus 10 degrees, roughly the average temperature in wintertime until March. Summertime, it's up over 30-some degrees. Over a 40-degree change of temperature there. Cleveland, look at it. Inland, 28. Average temperature in the month of January, 73. So over 40-some degrees there. But let's take a look at one other place, Seattle. 40 to 60. Only 20-degree change. Why is that? The ocean is a tremendous absorber of radiation, of the Earth's radiation, of the sun's radiation. And so it keeps the temperature fairly moderate, especially on the western coast of a continent like Seattle is. So the air that comes in off the water doesn't change a lot in temperature. So the temperature stays pretty constant. I'm on the East Coast over here in Virginia Beach. We do have a little more change because we get some wind off the land at times. But the ocean, it really has an impact, especially in the fall and even in the spring. The ocean's colder in the spring. We can be colder than we would be if we were inland. In the fall, we can be warmer than if we would be than we're inland. We talk about radiation going back out of the Earth and the atmosphere actually controlling what you see. You'll notice on a satellite nowadays, there are what they call bands. Band 1 is blue, visible. It's basically 0.47 microns. Did you know there's a band 2 that's red, 0.64 microns? This is more what we're used to seeing if you were to look up at the sky. Here's band 3, near infrared. Another infrared. Oh, band 4 is a higher up. This actually sees higher, tops of the clouds. Another band, it looks basically, this is what the snow is reflecting. So you can actually see various wavelengths relating to the bands that you would get radiation coming out of from the Earth. So I just wanted to give you an example how the satellites now, the weather satellites, are utilizing the knowledge of what infrared radiation radiates from the Earth to help us understand the whole structure of the atmosphere. 3 dimensions again. So I hope you got something out of this, and let me know if you have any questions.